You're able to hear me, right? Hello?
Yes,
Uh,
I'm here.
you're able to hear me, right? Okay. Are you able to see my screen?
Yes, yes.
Okay. Okay. Just a minute. I'll just yeah, it already started recording. So let's get on to the session. So did you write gate this time?
No, no,
Okay, fine. Okay, this is the first time you're attending the session?
no. Previous I am
Okay.
attended, ma'am.
Okay. I mean the first session you attended.
Yes, yes,
Okay. Did you go through the lectures of week 4?
yes.
You went through the
Week four, second class. I am attended. First
okay.
one and second one.
Okay. So let's go on to the session. So I welcome you for the week 3 live interactive session for the chemical reaction engineering 2. The course instructor is Professor Ganesh Vishwanathan, and live session is taken by myself, Kritika, PMRF Research Scholar, IIT Madras. Now, before getting on to the session, so we'll, as usual, we'll go through a recap of lectures of week 4. So, what were the contents of week 4 till whatever you have gone through?
Week four lecture.
Yeah.
Week four choice of a reactor like deactivation reactions. That's the topics.
Okay. 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 So, you didn't go through further, is it?
Uh, that means.
No, after that, that was the first lecture. I mean, lecture
Yes,
16. Or,
that was the first lecture. Slowly decay, moderate decay.
okay.
That's it. First lecture must attended.
Okay.
Second, I am not going.
Okay. So, you just covered the lecture 16. Okay. So, yes, as you said, lecture 16 was on catalyst deactivation. On the lecture covered on reactor design. So initially it covered on the fluidized CSTR. This was followed by, as you said, the choice of reactor for different level of decay, like whether it is slow decay or moderate decay or fast decay. And then some rate expressions were also derived based on the which reactor suits for each of the case. Okay.
Okay.
Uh,
Okay.
yeah. And then lecture 17 was on diffusion effects. So the diffusion effects were introduced. So do you remember what are the steps in a catalytic process?
Mm,
This was covered in the week 1 lectures. It has, do you remember number of steps?
yes, 7 steps.
Yes.
Steps. External diffusion, internal diffusion,
Yes.
adsorption, desorption, diffusion, external diffusion. These are the 7 steps.
Yeah, it
Am I
is
right?
actually external diffusion, then followed by internal diffusion of the reactants. Then it is
Yes.
adsorption of the reactants on the catalyst surface, and then surface reaction,
Yes. Yes.
and then desorption, followed by
Desorption.
internal diffusion of the products from inside of the pore to outside into
Okay.
the bulk, and then outside of the catalyst surface, and then from catalyst surface to the bulk. So that is
Okay.
again one more external diffusion. So there are two sets of external diffusion and two sets of internal diffusion. So the lectures from week 1 to 3, it covered mostly
Yeah,
on the
ma'am, one doubt.
yeah.
Adsorption is reversible. Internal diffusion, surface area. The figure showing adsorption reversible, like any possibility?
Yes, the adsorption steps are reversible. Okay.
Oh, okay.
Yeah, but there are also cases where this adsorption or desorption cannot be reversible also. That's what where your pseudo steady state concepts comes into picture. It
Yeah,
was
yeah.
right. Do you remember, if any one of these steps is not reversible, then we assume a pseudo steady state where the reaction rates of the formation of intermediates was assumed to be zero.
Okay.
Okay, so
Okay, thank you.
yes, yes. Okay.
Okay,
Yeah.
clear.
Okay, fine. So can we proceed?
Yes, yes,
Yes.
please.
Yes. Okay. So the lecture 17 was on diffusion effects. External diffusion, when what happens when in case of external diffusion, and then what happens in case of an internal diffusion if they are rate controlling. The concept was introduced, and then effective diffusivity. The concept of effective diffusivity was introduced. Because why do you think the concept of effective diffusivity is needed?
Mm,
Any guess? I think some background noise is coming, I guess.
mm,
Some
okay.
some sieving kind of noise.
മിറ്റടിക്കുക എന്താ പറയാ. I am basically a Malayali from Kerala.
No, no, I'm hearing some background noise of some sieving or some.
Yes,
Uh,
എന്താ പറയാ, സീവിങ്.
okay, okay, okay,
I don't get this that English word.
okay, okay. Okay, okay. But you should have come across this in mechanical operation, separation, right? Or I think someone is doing this separation of that husk from rice or something at home.
Ah, yes, yes.
Yes, that noise is coming actually in the background. Okay,
Okay.
okay, uh, okay. So, why do you think this concept of effective diffusivity is needed? You have a particular catalyst. Okay,
Okay.
it is having pores. Obviously, catalyst will have some pores where the active material is impregnated, right?
Yes.
And now we are introducing the concept of diffusion effects, which means the transfer of the mass transfer of the reactant species through the catalyst is going to control the reaction. Okay,
Okay. Okay.
so why is this effective diffusivity needed? Can't we just use the normal diffusivity, equimolar counter diffusion, the diffusivity of the equimolar counter diffusion as such? Why should we bring in a term called effective diffusivity? You want to take a guess or shall I explain?
Please explain.
Yeah. So, why are we introducing the concept of effective diffusivity is that, so as I said, this catalyst is going to have some pores, right? So,
Okay. Yes.
if you consider, say, for example, a spherical catalyst, so it may have different pores of different, sizes, right? And, and especially when you have this decay of catalyst and all, we have, come across this sintering where the pores may get clogged, or, there might be some agglomeration and all, right?
Yeah.
So, we cannot as such take a normal diffusivity. So we have to bring in these kind of resistances that are coming into the diffusion of the material, right? And that is why the concept of effective diffusivity is introduced, where these restrictions, say for example the pore diameter, and the ratio between the pores and the void, sorry, the solid area, that is the voids and the solid area, So these are all brought into picture. Okay, that is why we have the concept of effective diffusivity uh, in the diffusion controlling reactions. Okay,
Okay.
catalytic reactions. Not only in diffusion controlling catalytic reactions, but in anywhere, if it is going to happen in some kind of solid with pores and all, no, we bring in this concept. Okay.
Okay.
Okay. So in lectures 18, the diffusion, internal diffusion effect was further, it was further discussed, where there was, model development, was introduced, and the model development was based on the shell balances, and also what are the boundary conditions for such a shell balance model developed, was all discussed in lecture 18. And lecture 19, this model which was developed was non-dimensionalized, and then a concept called Thiele modulus was introduced. Okay, and this
Okay.
further, for this non-dimensionalized model, what happens to the Thiele modulus in case of a first order reaction was further discussed in the lecture 19. Okay, and the last lecture, uh, it contained on the concentration profile, basically the solution for this model. So the internal diffusion, the model for the internal diffusion effect, so we develop a model, so obviously we need some solution, right, for that model developed, so that we are able to find certain parameters and get insights from the models, right? So that was done for the first order reaction, and the concentration profile was sketched. Okay, and also what are the insights from this concentration profile that is obtained, okay, was discussed. And finally, the internal effectiveness factor, the concept of internal effectiveness factor was introduced. Okay, so internal effectiveness factor is nothing but what is the reaction rate, actual reaction rate that is happening to the reaction rate when reaction happens at the surface conditions. That is what happen, when the reaction, when inside of the pore is also having the same temperature and same concentration of the reactants uh, as such as that of the surface, then uh, what will be the effective performance that was introduced. Okay, are you there?
Yes. Yes. Okay.
Okay, now let's move on to the week 3 practice assignment. Now, identify the reactor and the type of decay process it can be used for. So, I'll be showing you two reactors. You have to identify what are these two reactors, and then for what type of decay process it can be used for. So, option A shows some reactor. So, this small portion is the reactor where the feed is entering from top and the product is from bottom, and then the catalyst actually it is it moves from the reactor into a section, it is a kiln where air is also passed through, and from here it is airlifted to through a separator, and then it is fed back to the reactor. Okay, uh,
Yes.
so what type of reactor is this?
Moderate decay reactor. Hello.
Okay.
Mooring bed reactor.
Can you repeat?
Moving bed reactor.
Okay, why do you say it is moving bed reactor?
Um, because regenerated catalyst then lifted to separator, killer regenerated, then the to separator that's moving അങ്ങനെ എന്തോ ഒരു
Yeah, yeah, I get you. Yes. So what happens in this case is that the catalyst bed, it is actually moving from reactor to the kiln and to the separator, and then finally back to the reactor. So there is a continuous movement of this catalyst bed. That is why it is moving bed reactor. In this process, it is getting regenerated continuously. And what type of decay process it can be used for?
moderate decay.
Yes,
Right.
correct. For moderate decay, moving bed reactor can be a preferable choice. Okay,
Okay.
what is option? Sorry, the figure B signifies. It shows some fluidized catalyst pellet, and there is a preheater uh, where at the entry there is some temperature T naught, and at the exit there is some temperature T. So, what is this reactor? And for what type of decay it is used for?
The second figure shows a reactor. That's you ask.
Yes, yes. What is it? For which type of decay it is used for? What type of reactor it is, and based on what concept, you can use it for this particular decay process.
That's the fluid bed reactor.
Okay.
Mm, then used in slow decay system.
Yes. Yes. As you said. So as you said, for the A, it is a moving bed reactor, this which is can be used for moderate decay, and then the setup B is a fluidized bed reactor with a preheater. So this is used for a slow decay, because in the case of slow decay, so what we can do is that we can have a preheater setup where the inlet feed can the temperature of the inlet feed can be uh, continuously increased. Okay, so that you maintain the required conversion as the catalyst gets decayed. So in order to maintain the conversion, we use a temperature time trajectory and keep on increasing the temperature of the incoming feed. Okay.
Okay. Okay.
Yeah. Now let's get on to question number 2. So question number 2 has two parts. Part A is a dash accounts for variation in the cross sectional area that is normal to the diffusion. So which parameter does which that accounts for this variation in cross sectional area? And the part B is ratio of actual distance traveled by a molecule between 2 points to the shortest distance between those 2 points is, what are these? So you can choose from the four options given is the diffusivity, tortuosity, porosity, or constriction factor.
Actually, ma'am, I don't know.
Okay, okay, just tell me, uh, just you understood the two sentences, right? So
Yeah.
under which concept these definitions and these parameters come into picture? We just discussed one concept where we have to take in these concepts. We just discussed when we were discussing the recap. Is actually these two definitions comes for two parameters which are involved in framing the effective diffusivity. Okay, because
Okay.
as I discussed these when I discussed this effective diffusivity concept, I told that and then the pores need not be of uniform diameter. It is not only that it need not be of uniform diameter, but the multiple pores need not be of uniform diameter, but within a single pore itself, no, there will be kind of change in area. Okay,
Okay.
so these concepts are discussed in that. And For question 1, the parameter that accounts for variation in cross sectional area that is normal to the diffusion is, it is the constriction factor. Okay. And
Okay.
the second one, the ratio of actual distance traveled by a molecule between 2 points to the shortest distance between those 2 points is, it is tortuosity. Because the path is not smooth, it is tortuous path. Okay.
Okay.
So these are the answers. So you can just figure out, identify from these figures. So in the case of A shows the pore constriction. So the pore need not be of a uniform cylindrical pore, right? It can have these kind of path. Okay, so this area is different from this area, right?
Yeah.
So we have to bring into the formula of diffusivity, the effective diffusivity, this kind of changes in area also, right? Because the molecule entering will have to phase through this change in area. So when the molecule enters in this area, it will be able to pass easily, whereas when it comes to this area, it finds difficulty. So we have to bring in these resistances also, okay, when we are considering the effective diffusivity of a particular species. So this constriction factor, which is denoted by sigma c, it is a function of a parameter called beta, which gives the area of the largest cross sectional area to the smallest cross sectional area in that particular pore. Okay, and when these two area are equal, then obviously your beta is equal to 1 and your constriction factor is also equal to 1. Whereas what happens is that when this A2, if it is 10 times higher than that of A1, then how do you think it will affect the sigma c? It will definitely have an impact on the constriction factor, and what it becomes is that the constriction factor becomes zero point 0.5. That is, it is nearly halved, right? When the area becomes the largest area is 10 times the smallest area within a pore. Okay, so we could understand the impact of the geometry of the pore, right,
Okay.
when a particular diffusion is happening. And the second thing is the tortuosity, as it as it is mentioned in this question. It is the actual distance traveled by a molecule. So if you just see, this is the free path available for the molecule to travel. So consider this point A and B. So if a species, some reactant comes into this space, it cannot go directly to this point B, right? It cannot go via this route, which is the shortest route. It will go through this route, the longest route. Okay, the actual route is this, whereas the shortest route is this. So this ratio of the actual path taken by the molecule uh, to reach B from point A to the shortest distance between A and B is defined by tortuosity. Okay.
Okay.
Yeah, now let's get on to question 3. Delay modulus is a measure of, is it a measure of surface reaction rate to diffusion rate, or is it diffusion rate to surface reaction rate, or is it adsorption rate to diffusion rate, or is it diffusion rate to adsorption rate? Do you have any guesses? I think you didn't go through, right?
No, it didn't go.
Yeah, okay. So let me say, it is actually the ratio of surface reaction rate to the diffusion rate. Okay, so uh, when this is the actual formula for the Thiele modulus. Thiele modulus is actually given by phi n. So the square of the Thiele modulus is given by this equation. So which is kn into r square into CAS power n minus 1 by dE, where kn is your specific reaction constant, r denotes the characteristic, length scale. Okay, here it is actually the radius. Okay, and DE denotes your effective diffusivity, and CAS is your surface concentration of the species A. And if you slightly modify it, you will get into this kind of a formula. So which is nothing but, if you just look into the numerator, it is nothing but specific, as I told, Kn is a specific reaction rate constant. That means the numerator denotes your surface reaction rate, and obviously De is your effective diffusivity. So your De denotes your diffusion rate. So it is nothing but Thiele modulus is a measure of your surface reaction rate to the diffusion rate. Okay.
Okay.
Yeah. Now let's go on to question. So to carry out a particular catalytic reaction in a reactor, it was decided to coat the precious metal, say for example platinum, okay, only close to the external surface of the spherical catalyst pellet. So the spherical catalyst pellets, say we can say, so you would have come across this denomination, that platinum over Al2O3, platinum which is impregnated on alumina and all, right?
Yes, yes.
Yes. So what they have decided is that they have carried out some particular experiment. So based on a insights of some experiment, they have decided, what they have decided is that, so this obviously, consider a spherical catalyst. Okay. Consider some sphere of alumina. Okay, this alumina sphere will have some pores, right? Where the catalyst, the platinum, can be placed or coated or impregnated, right? Hello.
Yes, yes. Yeah.
So what they have decided is that, if you just consider, see, if, let's consider a pore, and if you just consider that pore, they have planned to coat only near the pore mouth, or to certain extent near the pore mouth. Okay, surface of the pore only they have planned to coat the precious metal. They performed some experiment, and from the insight of that experiment, they have come to such a conclusion. Okay, so what information from the experiment, you know, made them decide to coat the precious metal, say for example, platinum, only closer to the external surface of the catalyst pellet. So can we just see what experiment that made them, get such information? Before that, I just want to ask, why do you think, this coating of the metal, the decision on coating of the metal becomes very crucial? Why is it that they have to perform some experiments, and they have to, get some insights, and based on that, for to when they are designing the reactor, they could coat the metal either fully inside the catalyst pore, or only in, up to certain extent? Why is it this decision very important? You can get it from one word in the uh, you know uh, question itself. They have to make such a decision because these are precious metals, like platinum and all, no, their availability and their cost is too high, right? So
Yes.
a wise decision should be taken. Say for example, I just coat the platinum metal completely in the catalyst, but your reaction is not going to use that entire, make use of that entire platinum that is coated. Then it is waste of money, right? And also, we have also discussed on catalyst decay and all, so that will get decayed also. So you lose the metal, right? Which really impacts on the cost of the process, right? So we have to take a wise decision on how to coat the catalyst also. So for that, the decision can be taken based on the concept of Thiele modulus and the concentration profile of the reactant species inside the spherical catalyst. So as is, as we discussed in the previous question, so Thiele modulus gives the ratio of the surface reaction to the diffusion rate, right? Hello.
Yes, ma'am. Okay.
Yeah. So from that, what we can actually get is that the concentration profile inside the spherical catalyst. Okay. So you can get some concentration profile like this. Okay. So what happens is that when the Thiele modulus is very high, if Thiele modulus is very high, we can just look into the formula. So if the Thiele modulus, if phi n square is very high, that means your diffusion is very slow, right? Your denominator should be very small, right? If phi n square should be very large, then your denominator should be very small. Correct? That means
Yes,
your
okay.
diffusion is very less compared to your surface reaction rate. So what happens in that case? As soon as your reactant sees that catalyst surface, immediately the reaction will happen, and the reactant will not even diffuse completely inside the catalyst pore, right? Because the rate of reaction is very high compared to your diffusion rate, and that is why you can just see in the concentration profile at large Thiele modulus, your concentration of the reactant you know drops to 0 before reaching R is equal to 0. So if you just look into this graph, this gives this graph is plotted on concentration of A versus your the characteristic length, that is the pore diameter. Okay, when R is equal to R is the external surface of the catalyst, and R is equal to 0 is the center of the catalyst. Okay, and the y-axis gives Ca by Cas, which is nothing but the concentration at any point inside the pore of the catalyst to the concentration at the surface of the catalyst. So obviously it will start with, the ratio will start with 1, right, at the surface of the catalyst, right? Hello.
Yes, yes.
Yeah,
Yeah.
okay. So what happens at large, value of phi or Thiele modulus is that this concentration will drop to 0 before, you are reaching the center of the catalyst pore itself. That means there is no point or no reaction is going to happen in the center of the catalyst pore, right? Because your entire reaction might get completed closer to external surface of the catalyst pore itself. So this makes a very crucial insight of how much till what depth you have to coat the precious metal. So in this case, what happens, there is no point in coating the precious metal till R is equal to 0. So at some R is equal to some R1 itself, that if you have done the coating, then it will be fair enough so that the reaction will happen at the required rate, right? So that is what is the decision made based on the value of phi. Okay. Whereas when the value of phi is very small, if you look into the concentration profile, you could see that till R is equal to 0, there is some reaction happening, right? In that case, you have to coat the precious metal completely in the catalyst pore. And similarly, in the case of the medium phi also. Okay. Hello.
Yes, yes.
Yeah. Okay. Now, actually, if you just look into GATE 2016, no, a question very similar to the question we discussed now has been asked. So they've asked a question, there's a slight reframing of the question. They've asked, a porous pellet with platinum dispersed in it is used to carry out a catalytic reaction. Following two scenarios are possible. Scenario 1, platinum present throughout the pores of the pellet is used for catalyzing the reaction. Scenario 2, platinum present only in the immediate vicinity of the external surface of the pellet is used for catalyzing the reaction. At a large value of Thiele modulus, Which one of the following statement becomes true? So they have given 4 options. Since the reaction rate is much greater than the diffusion rate, scenario 1 occurs. Option B is, since the reaction rate is very much greater than the diffusion rate, scenario 2 occurs. Or since the reaction rate is much lower than the diffusion rate, scenario 1 occurs. Or option D, since the reaction rate is much lower than the diffusion rate, scenario 2 occurs. So, what do you think the answer for this question? We already discussed the whole concept. Which one of the statements are true? It is actually B, right? Because your Thiele modulus is large. That means your reaction rate is greater than the diffusion rate. That means scenario should is preferable. That is platinum present only in the middle, in the immediate vicinity of the external surface of the pellet is used for catalyzing the reaction. Okay.
Okay.
Yeah. Okay. Now let's discuss question number 5. Consider a first order catalytic reaction in a porous catalyst pellet. Given R is the characteristic length of the pellet. dE is the effective diffusivity. Kc is the mass transfer coefficient. K1 is the rate constant based on volume of the catalyst pellet. And Cs is the concentration of the reactant on the pellet surface. The expression for Thiele modulus is, what is the expression for Thiele modulus? So is it A, Kc into R by dE, or is it B, R into square root of K1 by dE, or is it C, R into square root of K1 Cs, K1 into Cs by dE, or is it D, R into square root of dE by K1? Which one is it? We just discussed the definition of Thiele modulus also. And this is actually a GATE 2017 question. What do you think? So we discussed that Thiele modulus is the ratio of surface reaction rate to the diffusion rate, right? And here they have given the surface reaction as a first order reaction. So what will be the formula? You want to take a guess? Because we already discussed the formula for Thiele modulus also. Square of Thiele modulus we discussed. You just have to incorporate this first order catalytic reaction in the reaction rate term. Are you there? You want to take a guess?
Yes. No, ma'am. Go through the lecture.
Okay. So it is actually option B. Why is it option B? We'll just go back to the previous question and find out. So phi n square, which is nothing but the square of Thiele modulus, is given by Kn into R into CAS power n by dE into CAS minus 0 by R. Right?
Okay.
Yeah. So now it is your first order reaction. That means n is equal to 1. Right?
Yeah.
So CAS power 1 divided by, there is one more CAS in the denominator also. Two concentration, I mean, say there is a concentration term in the numerator and concentration term in the denominator. So both gets cancelled. Right? And then again this R, it moves to the numerator. So it becomes R square into K1 by dE. So which is nothing but phi 1 square. So your phi will be square root of K1 by dE whole multiplied by R. Right? That is what is the answer shown. Okay, simple mathematics. right?
Okay, okay.
Yeah. Now let's get on to this question. Question number 6. When the impurity cumene hydroperoxide is present in trace amounts in a cumene feed stream, it can deactivate the silica alumina catalyst, over which cumene is being cracked to form benzene and propylene. Okay. The data was taken at 1 atmosphere and 420 degrees centigrade in a differential reactor. Okay, the feed consists of cumene and a trace of cumene hydroperoxide. The cumene hydroperoxide concentration is 0.08 more percent. And from the data taken, in a differential reactor, they have, identified the decay to be a first order decay independent of the reactant, and product concentration independent of the reactant and product concentration, with the decay constant Kd is equal to 4.2 into 10 power minus 3 second inverse. Fine. So they have, they have done some experiment in a differential reactor, and they have found the decay rate is a first order decay, and it is independent of the reactant and product concentration also, and the decay constant they have determined. Okay, and as a first approximation, we shall neglect the denominator of the catalytic rate law. Okay, and consider the reaction to be first order in cumene. Given that the specific reaction rate with respect to cumene is K is equal to 3.8 into 10 power 3 mole per kg fresh catalyst uh, uh, per second per atmosphere. The molar flow rate of cumene is, the cumene purity is 99.92%, and the trace impurity is 0.08%. Okay, and the molar flow rate of this is 200 mole per minute. The entering concentration is 0.06 kilomole per meter cube. The catalyst weight is 100 kg, and the velocity of solids is 1 kg per minute. Derive the expression for conversion of cumene in a moving bed reactor. The question they have asked is what will be the expression for conversion with these parameters in a moving bed reactor. Okay. So now let's proceed with the solution. Okay. So they have given that cumene gives benzene plus propylene. Okay, here cumene is represented as A, benzene is represented as B, and propylene is represented as C. Okay, and mole percent of cumene is 99.92, and mole percent of the impurity cumene peroxide, which is going to decay the catalyst, silica alumina catalyst, is 0.08%. And the pressure of the system is 1 atmosphere, temperature is 420 degrees centigrade, which is nothing but 693 Kelvin. And then the decay constant, they have given it as 4.2 into 10 power minus 3 second inverse. And then they have mentioned that the decay rate is first order, and it is independent of the reactant concentration and product concentration. That means dA by dt is equal to, it is kd into A, right? And then integrating the expression, you will get the expression for activity as activity is equal to exponential of minus kd into T, the first order relation, right? That is what they have mentioned. And then next they have given the reaction rate constant K. Now what the rate expression, how will it be? So they have said that it is a first order with respect to cumene, right? So the reaction rate expression is minus Ra dash is equal to K into activity into partial pressure of A. Can you just tell me why did I use partial pressure of A instead of just concentration of A? What made me choose partial pressure of A for the amount of reactant instead of choosing Ca? Why did I choose Pa initially to write the expression? I could have directly expressed as K into A A of T into Ca, right? Correct? Are you there?
Yes, yes.
Why did I use partial pressure? What you know term in the question gives a hint that partial pressure should be used instead of just concentration directly. It is actually in this page. There is one term from which you can actually identify that we should use only partial pressure in the rate equation instead of concentration. It is actually your atmosphere mentioned in the unit of rate constant. Okay, so the from the unit of rate constant you can actually identify what term of concentration we have to incorporate, whether it should be partial pressure or it should be direct concentration. Okay, since it is mentioned as atmosphere, so we cannot use directly as Ca, we have to use it as partial pressure of A. And then I have rewritten the expression. First I have incorporated the expression for activity by mentioning exponential of minus kdt, and then I've used the ideal gas law to rewrite partial pressure in terms of concentration, Ca into RT, right? Where R is your universal gas constant and T is your temperature. Fine, you're able to get it.
Yes, yeah, okay, okay.
Yeah, so we have to be very conscious in writing the rate expressions also. There will be certain hints in the question itself, uh, so which can from which we can actually derive the rate expression with the corresponding rate expression. Okay, so that is what I have explained, where I've used the ideal gas law. So Pa is equal to Ca into RT, and then what's the value of R? Again, value of R we have to choose based on the set of units used in the given, right? Here we have atmosphere, liter and all those things. That is why we have expressed R as 0.082 atmosphere liter per mole Kelvin. Okay, if the
Okay.
units are different, then the value of R will also be different. Okay, you have to consider these things while writing each and every term. There should be always be unit consistency. And then they have given inlet molar flow rate is 200 mole per minute, which again I have converted to mole per second, because here your kd and all it is expressed in second inverse. Here also k is having your reaction rate constant is also having second, so I'm just converting it to the to have unit consistency I'm converting moles per minute to moles per second. Similarly, your initial concentration Ca naught also I'm just converting it into uh, moles. It is actually 0.06 mole per liter. It's not kilomole per liter, because when you are converting kilomole per meter cube to mole per liter, so here also there will be 10 power 3 and denominator also 10 power 3 will be there, so it gets cancelled. Okay, and then W is the weight of the catalyst, and since it is a moving bed reactor, they have also given the flow of catalyst also. It is 1 kg per minute. Again I have just converted into kg per second. Right, now we have to write the design equation for moving bed reactor, right? Because they have asked to write the expression for conversion for the moving bed reactor. Correct? Hello?
Yeah, I'm here.
Yeah. Okay. So the design equation is dFA by dW is equal to minus RA prime. And then I'm just rewriting the expression where I'm replacing FA with FA naught and X conversion, right? So I'm getting dx by dw is equal to minus RA prime by FA naught. And then we have a time term in the decay constant, decay, right? Decay expression, right? So now we have to convert that into some known parameters. So since it is a moving bed reactor, we can get the time from weight of the catalyst to the flow rate of the catalyst, right? So it is kg by kg per second. So you will end up in time term. And then I'm just incorporating the rate expression for the reaction rate, expanding the rate expression. And then the time term is replaced by its corresponding expression W by US in the design equation. And then now there's a concentration term Ca. So now this I'm modifying it to the known term expressions or parameters that can be derived. So here I have written Ca is equal to Fa by V, where Fa is the molar flow rate by volumetric flow rate, and then that is equal to Fa naught into 1 minus x by V naught into 1 plus x. Why have I written as V naught into 1 plus x? Do you have any clue? This you would have done in your reaction engineering 1. If you just look into the question, you have A gives B plus C, right? There is change in the moles, right? So that is what I have accounted for, right? So we can write it as V is equal to V naught into 1 plus epsilon x, where epsilon will give the change in the volume expansion, right? Which you have done in your reaction engineering 1. So epsilon is equal to 2 minus 1 because 2 components minus 1 Q mean in the initial inlet by 1. So that gives epsilon value as 1, and that is what I have incorporated in the Ca expression. Right? You are able to follow?
Yes, yes.
Yeah. Okay. And then I'm just incorporating every other term in the design equation. Once you incorporate all the terms in the design equation, you will get an expression like this. Okay. And then I'm rewriting the expression, bringing the similar terms in one side. So 1 plus x by 1 minus x into dx is equal to k into exponential of minus kd into w by us into ca naught into rt by fa naught into dw. And then we have to integrate it from 0 to x in the left hand side and 0 to w in the right hand side. And once you integrate, you will get an expression for this. So from this you can find out what is the conversion, right? Correct? You are able to get it.
Yes.
And since they have given all the values of K, Ca naught, R, T, U, S, everything, you can incorporate and find out what is the actual conversion is also. Okay? So
Okay.
few things you have to look into this question is that you have to see what kind of expression you have to use for a rate equation, which you can get hinted from your reaction rate constants units. Okay. And similarly, uh, you know uh, what is the expression for your activity? They have said It is first order with respect to activity. Decay rate is first order with respect to activity, whereas it is independent of the reactants and products, right? So that is why you get into this expression. And then you have to replace the time term with the uh, total catalyst amount and the catalyst flow rate. And similarly, the expansion factor comes into picture, right? So once you incorporate all these concepts, sorry, you will arrive at what is the expression for the sorry what is the expression for the conversion. And when you incorporate the values given, you will actually get to know what is the conversion. Okay. Hope you are clear, right?
Okay, clear.
Yeah. Okay. Now let's go on to so a small discussion on the uh, previous week assignments. I think the week 3 assignment was the deadline was over on 15th February, right? Were you able to submit the assignment?
Yes.
Okay. So you found you were able to solve all the questions.
Yes. Yes.
Okay, you were able to solve. Okay. Okay. Let's actually solve for the benefit of others also. Okay. I think the answers are given, but how to approach the answers, I think that is not mentioned in the answer link, right?
Right.
Yeah. So, okay, let me read through the question. Now, since you have already answered and submitted the assignment, just say me how to approach this. So, a few questions were just theoretical, right? It is based on some definitions and all that was discussed. So I'm not discussing those questions. I'm just discussing the problem based questions. Okay. The second question was such a question. So an isothermal first order gas phase reaction where A is giving B is carried out in a batch reactor using a catalyst with rate constant K prime. The reactor initially contains pure A. The rate law for the reaction is separable. The rate of the catalyst decay is zero order with respect to activity, with rate decay constant being Kd. The weight of the catalyst is W and volume of the reactor is V. Assuming constant density, find the conversion as a function of time. How will you find the conversion as a function of time? How do you start this problem? You solve this problem?
No, mom, I can't do this.
You didn't do this, huh?
No.
Okay, okay, you were not able to solve this problem. So, how do you approach this problem is that, so first of all, they have given it is the reaction is carried out in a batch reactor, right? And in the question they have asked find the conversion. That means immediately you have to write the performance equation for a batch reactor, correct? So, writing the performance equation. So here the reaction is in a catalytic reaction. So with respect to weight of the catalyst, you have to write the rate law, correct? That is why you are using Ra prime in the expression. So the expression is Na naught into dx by dt is equal to minus Ra prime into W, since it is with respect to catalyst, right? Now, once you write the uh, expression performance equation, then they have given it is a first order reaction, right? But there is the activity of catalyst also involved, because they have given some expression for decay of catalyst, right? So obviously we have to get incorporate that catalytic decay also into the rate law expression. So minus Ra prime is K prime into A of T, activity into the concentration of A, because they have given it as a first order reaction. Okay. Now we have to rewrite Ca in order to get in terms of the conversion form. For getting the conversion term. So Ca is nothing but Na naught into 1 minus x by V. Right. So once you next what is the rate of catalyst decay? So the rate of catalyst decay, they have given it as zero order decay, right? That means minus dA by dt is equal to kd, some constant. And then upon integrating, so integrating between the limits 1 to a. Why have I used 1 to a in the left hand side? The limits of 1 to a, because the catalyst activity will start decreasing from 1 to some value over the time. That is why initially, initial value, the lower limit is 1 and the upper limit is some a. Okay. And the right hand side is 0 to t. And on integrating that expression, you will get activity A of t is equal to 1 minus kd into t. This is just normal integration, right? And now we have to incorporate all these, what is the expression for Ca, the expression for activity, everything in the performance equation of the batch reactor. So you will get Na naught into dx by dt is equal to k prime into 1 minus k dt into Na naught into 1 minus x by v. And then Na naught gets cancelled. And then you will get an expression where you can, bring in the similar terms together. So dx by 1 minus x is equal to k prime into w into 1 minus k dt into dt by v. Again now you have to integrate. So once you integrate, you will get an expression ln of 1 minus x is equal to k prime into w by v multiplied by 0.5 into kd into t square minus t. Right? It is just simple integration, because integration of 1 by 1 minus x is nothing but minus ln of 1 minus x. And here again in the right hand side, you will, when you apply the limits and things, so you bring in that negative sign in the right hand side, so that you will get it as, initially you will get it as t minus 0.5 k dt into t square. So this left hand side minus, you're bringing it into right hand side, and then you will finally get into this expression, which is what is the answer. Okay, now you understood? Hello?
Yes, clear.
Clear. Okay. Okay. Now, the next question, was fourth question, which was a problem-based question. The activity of the catalyst as a function of time is given by A is equal to 1 by 1 plus A t power 0.5. The catalyst activity with time for light gas oil cracked at 750 degree Fahrenheit is shown in the table below. Okay, they have given time versus activity data. So observe that the above relation can be modified to a suitable linear form, and find the constant A using the obtained data. So what we are supposed to do, we have to linearize this expression and then use these data. So once we linearize, we can plot the given data and then find out what is the value of A, right? So how will you linearize the above expression? This assignment you have already solved, right? The answers are also out. How will you linearize this expression?
Just guess.
Hmm?
I'm just guessing the assignments.
Yeah, just guess it.
Yes.
Okay, you just guessed some answer and you have given, okay, you chose it, is it?
Yes.
Oh, okay. Now I understood. Okay. So actually the approach is, you have to take the inverse of the given equation. So there is this expression, you have to take the inverse. So when you take the inverse, the expression will become 1 by A is equal to 1 plus a into t power 0.5, right? Now it is in some linear form, right? It is y is equal to some a plus bx. It is of that form, right?
Okay.
So where x is nothing but your t power 0.5 and y is nothing but 1 by a. So when you plot 1 by a in the y-axis and t power 0.5 values in the x-axis, the slope of this data will give you, the intercept is 1 already. It is from the expression itself, you can find out the intercept is 1. So from this, you will get the slope. The slope value will be equal to a. Okay. So from the given data, what you have to do is that you have to find out t power 0.5. Okay. You have to take square root of the entire time data given, and then also the inverse of all the activity data given. And once you plot this data, you will get a straight line with an intercept at 1 and the slope value which is equal to the value of a. Okay, this is how you have to solve this question. So once you get the slope, you will get what is the answer is. Okay, this is what is the approach. Okay, now you got how to actually uh, do this problem, right?
Yeah.
Yes. Okay, good. Now the next question is question number 7. So for a heterogeneous catalytic reaction, the amount of coke deposited was found to be following the empirical correlation Cc is equal to A into T power n. The concentration of coke was found to be 2 gram per meter square and 8 gram per meter square at time t equal to 10 minutes and t equal to 100 minutes respectively. So find the value of n. So how will you find the value of n in this case? Here again, what you have to do is that you have to try to linearize this expression. Okay. So when you take log on both sides, what will happen is that, so log Cc is equal to log A plus n into log T. And because here in the right hand side, log of m into n is nothing but log of m plus log of n, right? Your basic logarithmic rules. Okay. So once you get this expression, now this expression is also in the form of y is equal to mx plus c, right? Where your y is nothing but your log c, and then your x is nothing but your log t, and m slope is nothing but your n value, and your intercept is log a. Okay, so you're being given two set of, so you have 2 points, right? So obviously you can draw a straight line, and then from the slope and intercept of that straight line, sorry, you you can find out from the slope you can find out what is the value of n. And similarly, from the intercept, you can find out what is log A, and taking that log inverse, you will get what is A, right? You are able to follow?
Yes.
Okay, okay, fine. Okay. So, any other doubts you have?
This
Actually,
question is once more, please, ma'am.
which
I
one?
don't get it.
This
Seven those.
this question. See, you have this expression, right? The concentration of the coke Cc is equal to A into T power n. So what you can do to linearize is that, so they have asked to find out the value of n, correct? So in order to find the value of n, so this is in some exponent of t, right? It is t power n. So as such, if you just plot, you will get some curve, right? So it might be very difficult for you to find out what is the value of n. So for that purpose, when you take convert this into a logarithmic scale, okay, taking log on both sides, so you will get an expression log of Cc is equal to log of A into T power n. Okay, according to logarithmic rules, log of m into n is equal to log of m plus log of n. So here it is log of a into t power n is equal to log of a plus log of t power n. Okay, again in the logarithmic rules, log of a power b is b into log of a. That is again basic logarithmic rule. So
Okay.
once you incorporate all these things, you will get into an expression log of cc is equal to log of a plus n into log of t, right? So when you just look into this expression, this looks a linear expression, right? Like your y is equal to mx plus c,
Let's
correct?
see.
Yes.
Yeah.
So where your c is the intercept and m is the slope. So here your log a is the intercept and n is the slope. So when you find the slope of the line, you will get what is the value of n, right?
Okay.
You can obviously draw a line because they have given 2 points. One at time t equal to 10, the concentration is 2, and the other one is t equal to 100, the concentration is 8, right? Even straight away you can find, right?
Yeah.
uh, and then if you just find out that value, you will get what is the slope and what is the value of n, right? Now is it clear?
Yeah. Clear.
Yeah, you have to incorporate mathematical lot of mathematical rules also. So you have to find when look into when you look into the expression, you have to find out, okay, when you just take the inverse of the expression, then it will get into a linear form. When you take log of an expression, then it will get into a linear form. Why do we get into a linear form is that it is easy to find out the unknown parameters, right? Some constants and all easily when it is in a linearized form. That is why. Okay.
Okay.
Yeah. This you will start do getting it faster when you start solving many problems and when you look into many concepts. So you will start recollecting all these things, but you have to be very sharp in your mathematical you know concepts as well to bring in these things so that you are able to solve these complicated problems as well. Okay.
Okay,
Any
ma'am.
other doubts you have?
I think.
Okay. uh, then it's done with the session.
Okay. Thank
So
you, ma'am.
thank you. So try to solve the assignment for. Hope this session it helped you in understanding it better, and please go through the lectures because lot of efforts have been put to uh, uh, take the videos of these lectures and uploading it. Okay, so make the
Okay.
best use of it. The professors take a lot of time, a lot of efforts have been put in, so please go through these lectures so that you will understand the concept better. And also try to go through the lectures before this live session so that you are able to uh, understand the problems which we are discussing in the session better, and you are able to at least guess these concepts, right?
Okay.
Okay. Okay, then have a nice day.
Thank
Good
you.
weekend.
Same to you.
Thank you.